So if the energy mass is smaller than the open threshold, like the bar threshold, then this is nothing but a bound state, like heavy fog and heavy fog. However, many XYZ states appear above this open threshold, where the scattering state should be considered. For example, in this case, D and D bar can be separated from each other. And in that, this is a scattering state, therefore, some bound state. This is very much different from the bound state. And here, we can find the resonance state. And in my presentation, or in my problem, I simplify the real relation to a very simple form. As a threshold, I consider only two thresholds. And we consider the two scattering states, which is denoted by G and E, named after ground state and the exciting state. And especially, we focus on the Feshbach resonance. Maybe you have already heard the Feshbach resonance in some courses or in some textbooks, in some articles. But this is nothing but the resonance structure, which is driven by the two-channel coupling problem. And in my problem, I like to see this Feshbach resonance in one-dimensional system. This is because the problem becomes very easy. And especially, the setting is something like this. So because we are in a one-dimensional system, we have the x-axis, and this is the energy axis. And normally, we consider only this state, ground state, but because we are now thinking of the two channels, we consider also exciting state, psi E. And the psi E, energy E and energy G is different. And however hard Feshbach resonance, if you have raised your hand. No? Okay. So this is the imagination of the Feshbach resonance. So suppose there is a ground state and we inject the energy. Then of course, then the ground state becomes excited state, but this excited state becomes ground state again by emitting the energy. However, when there is some interaction as a fine-tuning, we can find a set of bound state here as a bound state of this excited state. And this is the Kesa bound state because this is not a really bound state because it indicates the ground state by emitting energy. So this is a Feshbach resonance. And before going to the problem, I have to say a little bit more. Maybe I can skip, sorry. I want to skip here. And what is important thing is to understand the symptomatic behavior of the wave function. I think you have, almost you, have heard already in the normal quantum mechanical course about the resonance, about the scattering states. And in this case, the wave function is expressed by the superposition of incoming state and outgoing state. And we define the S matrix here as F plus F minus is a coefficient for the incoming state and outgoing state, and S is defined by F minus divided by F plus. And what we have to do here to find the resonance is to search a pole in this S matrix. That means F1 plus equals 0. And in this condition, we can forget about this incoming state, and we have only the outgoing state. And in the end, we can find this kind of momentum structure. And this is displayed in a figure like this. So let's see. So this is the going state. Therefore, we have only exponential I KPR. KP is some momentum, and bound states is nothing but the pure imaginary part of the KP. And there is an anti-bound state, so-called anti-bound state, and it's called the partial state. But this is not a really physical one because you see the wave function diverges at the distance. So this plus I plus I pure imaginary of momentum is a real bound state. And as another state, we can find a resonance state and also called anti-resonance state. But physically, this resonance state is good enough to be considered. And in this case, this is the imaginary part, and with minus the real part and minus the imaginary part. And in the momentum space, and you have to be careful that this momentum is extended to the imaginary plane, and normally the scattering state is on the real energy plane, but the bound state appears in the positive imaginary, real axis, and bound state appears in the positive imaginary part, and the resonance here comes here. And we have to be a little bit careful when we consider the energy, because the momentum and the energy is somehow related to K equals to root E with mass to M, mass M and to ME. And this root function is a two-variable function. Therefore, I think this is also maybe it has hard in the mathematical complex analysis course. But anyway, because this is a two-variable function, we need the two Riemann sheets. Okay? And when we turn twice on these Riemann sheets, we can just go around these momentum circles. Okay? And the bound states appear here in the, I think this is the first Riemann sheet, and the resonance appears in the second Riemann sheet. So upper half of this momentum is the first Riemann sheet, and the bottom half of this is the second Riemann sheet. So anyway, we have to be careful about this boundary condition. And then, with keeping those in mind, I'd like to see the scattering problem in matrix. Actually, this is not my original problem. I have brought some idea by Harry Lipkin, who is a very famous physicist, and he wrote very excellent textbook. This is not really the textbook, I think kind of by textbook, but anyway, you can find many interesting topics which is understandable to master course students also. Anyway, this is what I want to do in this maybe 40 minutes. And first, I'd like to ask you to solve this problem, zeros problem. Okay? And I suppose you can solve within 10 minutes, because this is very, in a sense, trivial, just confirmation what is known already. And this one, problem one, with the function potential, is also, I think you have already done some work in the undergraduate course, but it may take some time to remind yourself what you have done maybe a couple of years ago. And so I'd like to give you 15 minutes. And the first resonance is the main problem, so we need a little bit more time. So, and for each problem, I will give you answer step by step. So if you finish within 10 minutes, I will give you answer, and if you finish within 15 minutes, I will answer, and also. And sorry, before starting, I have to say sorry. There is an error in my program. Actually, in the page 5, problem 3.1, I typed U0 psi G0, but this should be removed. Instead, please add U1 psi G0 in the bottom line. I'm really sorry. Okay, so let's do the problem zeros problem for preparation. I think it takes only 5 minutes for you. And if you don't understand this problem, I'd like to explain more. So if you can do it by yourself, please keep doing it. But if you find it's a little bit hard to find something, then you may listen my presentation. Okay? So you don't know, all of you do not necessarily my this talk, but if you need, please listen. So for the preparation, we have to be a little bit careful because this is the property in the one-dimensional system, and we consider the parity conserving potential in our case. And therefore, the Hamiltonian is invariant under the parity transformation, and hence we can classify all the wave functions in two types. The first is the parity plus state, that means this is the apparently parity plus, and this is the parity minus. Therefore, if we interchange the x-axis, the wave function becomes minus. And in the case of parity plus, we can define this kind of wave function. So x is some typical distance at which the energy, the potential becomes zero. So if the small x is larger than x, this is a free part, but with some phase shift. And the right-hand side can be expressed by cosine kx plus delta 0 with a phase shift delta 0. And this 0 means the parity plus easy parity. And for the negative part, we can write the cosine kx minus delta 0. And it may be easy to check that this cosine k minus x is actually equal to cosine kx. And for the parity minus case, instead of cosine, we introduce the sine function. And the asymptotic behavior is due by sine kx plus delta 1, and 1 being the parity minus, in some sense, odd parity. And this left region is given by sine kx minus delta 1. And probably by just looking at those equations, you can find indeed psi k1 minus x is equal to minus psi k1. And to find some solutions, especially by using the S matrix, we have to define the S matrix in one-dimensional system. This is a little bit annoying thing because normally, I think in the normal course of the quantum mechanics, we define this function or this function and make some connections at the boundary. But to really define the S matrix, much better to introduce a radial projection or radial axis. And in this case, we can define that the R for theta, the mimicking some angles in three-dimensional system, but in this case, the theta angle has just two values, 0 or pi. And 0 means this direction, and pi means the opposite direction. Anyway, what is required in 0.1 is to show that cosine kr plus delta 0 can be expressed in this way by using the R function. And the psi k1r or something with some factor, this is actually nothing but a Lysander polynomial. And it can be expressed in this way. Okay? So maybe. And we have seen separately for even parity and odd parity, but in the 0.2 we can express in a combined way. So please forgive. And the final is a little bit complex, but anyway. So here we define the S matrix in this way. So this is nothing but this factor, the outgoing wave. And the partial wave amplitude can be defined in this way, SLK minus 1 divided by 2K. And this minus 1 means to subtract the trivial waves. Therefore, SL minus 1 means some scattering or interaction case. And I divided this by 2ik. This is just a mimicking the three-dimensional system. Anyway, so this is a kind of definition. And what I want to ask you is to show that so absolute value of this partial wave function can have a large value at some point, kr, which is defined by L sine delta LKR is equal to 1. And around this point, we can express the partial wave amplitude in this way, where the E is the positive energy, and ER is defined by KR in this way. And gamma is defined by this way. Anyway, please show that around this point, KR, the amplitude can be expressed this way. Japanese style, it's sometimes walking around. might find student upon some, we need some factor here. We need minus I.
So you say all minus I should be multiplied.
Overall. Okay, I think most of you did work, but anyway, let me show you because the time is limited. I have to show you. So our 0.1 apparently cosine k r plus delta 0 is half exponential I k r plus delta 0 minus exponential minus I k r plus delta 0. And which means if we extract some factors after plus minus I delta 0, then the remaining part is just okay, this comes here minus I k r plus exponential I to delta 0 exponential I k r. Okay, this is it. And what I did some mistake is that was this one. So let's look at only this k r plus delta 1. And in this case, this is 2 minus I. This is, I missed this one. Minus I divided by 2. And exponential I k r plus delta 1 minus exponential minus I k r plus delta 1. And then we get minus with minus I here, exponential minus I delta 1 plug into this, and so okay, because this is minus 1, so I change this plus I, then I get minus I k r minus exponential to I delta 1 exponential I to r. Okay. And by combining these equations, we can immediately see that the equation 11 folds. So this is not so problematic, also I made a mistake. But in the problem 3, this is a little bit annoying because so f L 0.3 to the moment. To ik exponential to I delta 0 k minus 1 and and to ik here and Sorry. So this is 2ik exponential I delta L. Therefore, here is exponential I delta L k delta k minus exponential I delta L k. So with this heat to I, and this makes 1 over k exponential I delta L, and I just with k and sine delta L. And what is required here is that the tangent delta L is close to 0. Okay. This is the definition of the resonance energy. But apparently, we don't find any cotangent structure here. So, we rewrite this in the following way. This is a little bit tricky, but we can confirm that this is indeed we produce this one, because cotangent is nothing but the cosine delta divided by sine delta minus I. Yeah. And k cosine delta minus I sine delta and sine delta here. And this is k exponential I delta sine delta. Therefore, in that sense, what is required in the problem is that this cotangent delta 0 becomes 0. I release this part. Then, what is the meaning of this nearly equal to 0? So this is an expansion actually around the 0 point. So I may not have been so kind to express this one anyway. So let me do it myself. Therefore, cotangent delta can be expanded around the point that cotangent delta becomes 0. This is the point KR. And because this is the Taylor expansion, we do the expansion about cotangent delta with KR and E minus ER. And the problem is to how to estimate this one, because this becomes just 0, right? So D, P cotangent is, can you say immediately how much it is? So anyway, this is defined, this is the definition, minus 2 divided to gamma, so at this KR, so this is the definition. In that sense, this is expressed by 2 divided by gamma minus, E minus ER. Okay, seems good. So I erase this part. So then, by putting this equation to here, we find that, so this is not really 0, approximately 0. So this is the expansion around the point. 1 over k is here, and 2 divided to gamma is here, and E minus ER is here, and minus I. And finally, we get this factor and E minus ER minus I, gamma divided by 2. So this is what I wanted to ask. But even if you couldn't find the solution here, this does not affect in the next problem. So because the time is limited, I'd like to go to the next problem. Okay. Is there any quick question? So please take this preparation part, is correct one, except for the sign in equation n. And then we go to the delta function potential. And I think this is much easier, I guess, but anyway, so if you can please start by yourself. And I'd like to give some explanation for the people who do not understand what is required here. Actually, what I want to do here is to find some bound state, and I introduced the delta type potential here, and this U0 is a positive number, and this 2m is just for the convenience of the calculation, and therefore we have a bound state here. And first, please, so that the equation, wave function psi k0 So this is just a schematical picture, so please do not take so much seriously about this wave. But anyway, for the wave function psi k0, please put that equation 17 forward. This is a little bit technical one, but this is very important to get the real solution. And so in the next, we consider the even parity solution whose asymptotic behavior is given by cosine kx plus delta 0. And please find that the phase shift is expressed in this way. Okay? So this determines the behavior of the phase shift for the arbitrary momentum. And third, so we consider the S matrix. And please show that this S matrix has a pole structure at the imaginary momentum, k equals I20 divided by 2. And also show that this is a bound state with binding energy Q0 squared divided by 8m. And this is actually the bound state because this is a positive imaginary number. Therefore, you remember that I have talked about the asymptotic behavior of the wave function, something like this. So this is our answer which we want. Anyway, please start to show the equation 17. And I forget one. So the final, please draw the graph of delta 0k as a function k. Okay. Of course, if you need, you can discuss with your friends, really, of course. I think some of you have done already, but due to the, and some of you may be doing still, but sorry, due to the lack of time, I have to go to the answer time. And the equation, the potential is something like minus u0 to m with delta function. And our Shigehiro equation is b squared dx squared plus, so by plugging this reaction to m u0 del x and psi each side. Okay. And what we do here is just integrate over, just integrate from minus epsilon to plus epsilon. And then we can get immediately something like this. B square dx square psi minus epsilon is nothing but dx. Is nothing but d dx psi minus epsilon. So this is just minus, and this psi dx epsilon minus d psi dx minus epsilon. And as for this delta function term, we get this kind of term, delta x psi x dx. So this is easy because delta function is here, therefore we just pick up only psi and 0. I forget to say that we take the limit epsilon goes to 0. Okay. And as for the last integral, this is just 0 because epsilon goes to 0, minus epsilon goes to 0, epsilon goes to 0, so we don't have anything. So as a result, we have minus 2m d psi dx epsilon minus d psi dx minus epsilon and minus q0 divided by 2m psi 0 0. So by removing this minus 1 over m and 1 minus over m, we get the final result d psi dx epsilon minus d psi dx minus epsilon plus u0 psi 0 is a 0. So this is what for I wanted. And what we want to do is here is to find the relationship between the phase shift and the momentum. Therefore, by just dragging the psi function cosine k x plus delta 0, so, and this is a positive energy part, and the negative energy part was cosine minus kx minus delta 0. Okay, this is what I have requested in the beginning. So in that sense, this psi, this derivative, d psi dx and at epsilon is minus k cosine, sine kx plus delta 0 with x equal epsilon, but because epsilon is a tiny quantity, therefore this becomes k sine minus k sine delta 0. Okay? And this also becomes this psi dx and at minus division, then the minus k sine kx minus 0 with epsilon minus division, then anyway this becomes k because this vanishes and minus minus sign makes plus sign and sine delta 0. Therefore, by putting those equations here, then we find that minus k sine delta 0 minus k sine delta 0 plus u0, and this sine 0 is nothing but cosine delta 0, 0. So minus 2k sine delta 0 plus u0 cosine delta 0 or 0. So you find immediately that tangent delta 0 is u0 divided by 2k. And as I said, the whole structure of this matrix is, as written here in number equation 19, sorry. So this matrix is, in this case, written by 1 minus I tangent delta 1 plus in the denominator and the numerator is I tangent delta. Okay, this plus minus sign is different. And by dragging this tangent behavior here, minus I u0 divided by 2k here, and u0, 1 plus I u0 divided to k here. And therefore, k minus I u0 divided by 2, and k plus I u0 divided by 2. And therefore, from this structure, we can find that k whole I u0 2 is actually the binding state, gives the binding state. And the energy is just k squared divided by 2m. Therefore, by dragging this, we can find immediately 8m here and u0 squared. And this is because the binding state. And the absolute value of the binding energy is u0 divided by m. And the figure of this cosine function, this function is a little bit, in a sense, simple, but just a little bit difficult, because here we have the delta 0 is arctangent 2k u0 here. But can you imagine the figure of the arctangent? So I erase, and I erase this part. So arctangent, normally arctangent is this kind of function, sandwiched by the region pi minus pi divided by 2 and pi divided by 2. But in this case, we have the k in the denominator. Therefore, this x-axis somehow interchanged. And as a result, we should have this kind of behavior. Something like this. And here is pi divided by 2. And this position, this finite position at momentum k equals 0 means the existence of the bound state. Okay. So this is the answer. But anyway, do you have any quick question? So if not, let me go to the final. Sorry, I and maybe let me go to the final problem. So this is the Feshbach resonance. But I use this kind of, this is not a real technique, but this kind of calculation in the Feshbach resonance. And again, if you can do the problem 3 by yourself, skip problem 2 and go to the skip problem 3, the Feshbach resonance. So if you can solve the Feshbach resonance by yourself, then do it by yourself. But I'd like to explain for the people who is worrying about what is asked here. But anyway, what we do is think of this resonance process and find the Tesha bound state. And to formalize this problem or setting this problem, we consider the Psi G state and Psi E state whose energy is given by G and E separately. And the first, I assume the attraction in the excited state here with the delta function. So this is looks like the situation in equation 1. But the real situation here is a little bit different because we also introduce the interaction part between this ground state and this excited state. This is nothing but the mixing state. And the strength of the mixing is given by U1. And U1 and U0 are different quantities. But here we assume that there is a function as well. And 2m factor is just for the easy calculation. And then this kind of setting can be formulated in the matrix way because we have two channels, therefore this equation given by 2 by 2 Hamiltonian. And this diagonal part is a kinetic term, but with the energy, some energy shift Eg and Te. And the potential term is given by this delta function with the coupling strengths U0 and U1. And according to this situation, the U0 appears only the right bottom panel, and U1 appears in the off-diagonal part. So this is what is asked here. And the question is to show first, so this is the equation, correct equation, that please show that if this equation holds 31 and 32. And I think this is another way can be calculated. And the second one is to assume we introduce the wave function for the ground state. We introduce, it looks like scattering states, and they are propagated because they are propagating. But for the excited state, we use this kind of wave function, and this K and Ke are in generally different momentum because energy are different. And the energy and the K or Ke are connected in this way. This is also, I think, in a sense, trivial. But in the following, we consider the bound state solution for psi E, whose energy is below the Ee. And this is a little bit special setting, but this simplification makes the calculation much shorter. And then, for example, in our case, because we are looking at this state whose energy is in between Ee and Eg, therefore, in view of psi E, this is nothing but a bound state. Okay. Therefore, the momentum of Ke is assumed to be I kappa E, with kappa E the real number, positive real number. And what is required here is to show that the phase shift for the ground state can be expressed in this way, equation 37. This is also in a sense analogous. And this is the final one. So based on this assumption or setting, you can calculate the resonance energy and decay rate by using the equations or formulas in the zero preparation. And anyway, please show that is 38, 39 form. Okay, sorry, I'd like to go to the answer time. But if you are keeping doing, please keep doing. And the Hamiltonian is minus dx squared, and the potential is to mu1 delta x here, and the Eg minus 2m1 dx squared minus u0 divided by 2m delta x, and here that minus u1 divided by 2m delta x. Okay. So this is our equation plus E. And we multiply Eg or Ee this way, and observe psi G, psi E. So if you write down a component E, then this becomes Ex psi G plus Eg psi G minus U1 divided by 2m delta x psi G equal to E psi G. And the lower part is
psi E, right? Minus U1 and psi E.
psi.
No?
Oh, sorry. Thank you very much. And this becomes minus 2m E squared psi E minus plus E psi E minus 2m u0 delta x psi E minus this one 2m psi g, e psi e psi e. And as we have done, we make a integration, okay, like this, but you may already remember that this becomes 2m, thank you very much, e psi e dx epsilon minus e psi e dx minus epsilon. And this term vanishes because we take the epsilon goes to zero limit. And we get this only this term to mu1 psi e 0. And this also becomes 0, therefore only. And for the latter part is dx, d psi dx e minus epsilon d psi dx minus epsilon minus 2m u0 psi e 0 and 2m u1 psi e 0 and 0. Okay. So this is in a sense trivial. So we insert the wave function to this. This is nothing but the boundary condition at x equals 0. And we insert our wave function here, and because psi g is supposed to be alpha cosine kx plus delta 0 or positive x. And for the negative x, this is alpha cosine kx minus delta 0. And psi e has exponential I with beta, but anyway, let me calculate it this way. Kappa e and with x absolute value. In this sense, we have the x here for the positive x, and for the negative x, we have beta exponential kappa e x, because x is negative. So this is our setting. And anyway, by dragging those wave functions here, maybe we can find immediately that this becomes minus 2m. This is analogous way. Alpha to alpha sine delta 0. Okay. And this is minus 2m with u1. Psi e is beta, so this is beta 0. And this way, this one is minus 2m. And because this is kappa e kx, but at the same time we get also kappa something like this. So this is a 2 alpha e. But this exponential becomes just 1, therefore only this one. And minus 2m u0 psi e 0 is just a beta, and this u1 divided by m is just alpha. Okay. So this is our equation. and let's remove the irrelevant to n. And then 2 cosine delta 0 alpha plus u1 delta equals 0. And I forget to k squared. Sorry. So this is 2k squared. And this is gain. Alpha is 2k squared and 1 coming from here and plus u1. Alpha no, only 1. Plus u0 delta is 0. Am I correct? So in order for that those two equations have a non-trivial solution, we have to require that the determinant should be 0. Therefore, 2k cosine delta 0 times u0 minus again then u1 cross 2k plus u1 is 0. Sorry, I forget. Sine delta 0. Just a moment. I have to calm down. Just a moment. Probably we need cosine delta 0. Therefore, sorry, I made mistake. Plus u1 sine delta 0 delta 0. Sine, yes. Sorry.
You can make lectures. I mean,
we should make a break.
I'm really sorry. This should be sine. This is cosine. And this is sine. And this is cosine. And here cosine. So 2k sine delta 0 with u1 cosine delta 0 alpha plus u0 cosine. Cosine delta 0 delta to 0, and therefore for determinant 0 this gives 2k sine delta 0 u0 cosine delta 0 minus u1 cosine delta 0 2k sine delta 0 plus u1 cosine delta 0. And I'd like to a little bit omit something. But anyway, from here, this, maybe I have to refresh my mind. From this kind of calculation, maybe something wrong. Sorry. We get the tangent delta 0 to k to kappa e minus u0 and u1 squared. And the process to get the solution of 3.3 is very actually straightforward. So we have given the definition of the resonance in 0.3, And in that sense, we can define the point that tangent delta 0 becomes sorry, cotangent. We can define the cotangent delta 0 is 0. And then from around this value, we can calculate this quantity minus derivative with respect to t at some this point. And actually, this gives the decay width, which is expressed in the 38 and 39. But sorry, because time is limited, I'd like to stop here. And so, thank you very much.
Okay. Thanks a lot, everyone, for participating, and thanks a lot for the exercise. We ran pretty late, so I would suggest that we have